Okay, we've seen the move structure and we've seen how to query it, and we really have just one task left, which is that we need to see how we can do that in constant time and without violating the other guarantees that we would like to have, like, for example, the big O of R space guarantee. And so I'm going to explain that here, and I'm going to follow roughly the argument that's in this paper here called RLBWT Tricks by Nathaniel Brown and Travis Gagey and Max Rossi. And this is a version of the explanation also that's in the original paper by Nishimoto and Tabe, but I'm going to follow a simplified version. Okay, we saw this example in the last lecture. This was an example where we had to do numerous scans in order to update the ID of the run that we are in when we go to do our update. So again, when we run the permutation forward, we start with a K and an I. The K is our offset. The I is the ID of the run that we're in, and we have to update them both. And updating K to K prime was easy, but updating I to I prime was a little trickier because we had to first follow what the Xi column told us to do, and then potentially we also had to walk row to row through the move structure until we got to the row that contained K prime. And depending on the example, I showed this example at the end of the previous lecture, sometimes the number of scans that we have to do from row to row through the move structure is actually excessive. So in this example, we needed, for example, when we wanted to compute the permutation for this offset right here, our K prime was offset 40, but then we needed to do these 9 scans to get to the I prime for the next iteration. Now, this was the worst case for this particular example. In other words, I chose this example because 9 was supposed to be a pretty high number. If I fill in for every single offset with respect to Q, how many scans would be required to get to the appropriate run of the move structure? It's going to be some number ranging up to 9. 9 was the worst of all the examples. Again, I wanted to show you a bad example. But we also have, some lower numbers in here. So for example, if we started like here, I guess that's like from the run head, that's offset 1, 2, 3. So from the run head, that's offset 1, 2, 3. That has 3 here. In other words, in order to update my I to I prime, I would have to scan forward by 3 rows in the move structure table. Okay, our goal is to reduce these numbers, right? So in this array, the maximum number is 9. We want to bound that by some constant. We want to choose a constant, presumably less than 9. Maybe we want to choose a constant to be 3 or 4 or something like that. And then we want to have a way of modifying the algorithm so we never have to do more than that many scans. So that's our goal today. The basic idea is we are going to split. So whereas we have our initial running permutation, and that gives us an initial number of, parallelograms, which is to say it gives us an initial number of rows in our move structure table, we need to be willing for there to be more rows than that. We need to take some of the initial rows and be willing to split them into a larger number of smaller rows. We need to take our larger parallelograms and turn them into a larger number of smaller parallelograms, but hopefully not so many of them that we violate the big O of R space bound. But the way we're going to get there is with splitting. Initially, we will pick as our constant threshold just the number 4, right? So we're going to insist that we never have to do 4 or more scans in order to get to our destination, just because that's the easiest way to show you the proof. But I'll show on a slide sort of toward the end, we don't have to just go by this threshold of 4, right? We can pick a different threshold. We have some flexibility in picking this threshold. Okay, so when we split a run, it's a little bit like we're taking the initial parallelogram and splitting it into 2 smaller parallelograms. Okay, so and the way we reflect this in the P and Q bit vectors is we have to set additional bits, right? Currently, the bits just reflect the heads of the run of the parallelograms in P and then their images in Q. But in order to accomplish this splitting, we need there to be more smaller parallelograms, which means we need to set more bits in P and Q. Okay, so here's an example. This is one of the parallelograms from our original example, and I'm showing you again, this is how many scans it would require to update I prime if K prime is at the corresponding position, right? So these K primes are trickier over here because if you just look, let me just draw some vertical lines. So for example, if we were trying to figure out what's my I prime if I landed here, that means we're here, but our run head mapped here, which means we have to fast forward twice, and that's why we have 2 here, okay? Sometimes I'll use the term fast forward for this forward scanning procedure. Okay, so let's say we wanted to attack those 2s. We thought 2 was too many scans to have to do. Well, then we might choose to split the parallelogram by setting these 2 bits to 1. All right, so we set this bit down here to 1, and we chose that bit because that bit in Q is at the beginning of this section where we had to do more scans. So we hope by splitting Q up this way, right, that we could reduce the number of scans. But it's not sufficient to just set this bit in Q, because remember, P and Q have a relationship, right? P marks the run heads for all the runs that are present in this running permutation, and then Q marks their images. So if we're going to set a bit in Q, in order for the P and Q to stay consistent, we have to set that bit's pre-image in P. In other words, we have to set pi inverse of that offset, right? Pi inverse of that offset. We have to set that corresponding bit with respect to P. And we can see which bit that is because I drew the whole parallelogram here. So you can see that this bit is at offset, 0, 1, 2, 3 into this parallelogram. And so we would set the corresponding bit here. And in doing that, we're essentially going to take what used to be one bigger block from this permutation and split it into 2 smaller ones. Okay, and once we've done that, now these are not so hard. So I've got 2's here. Those 2's are from before. The new number that we would put there would actually be 0, because now it's the case that for all these K primes, we don't need to do any scanning in order to find the corresponding I prime. In other words, now, since we have a new run head here, that new run head maps here, which means that all these bits map to the same run as the run head. So there's no fast forwarding required. Okay. All right. But this came at a price, right? We liked the block structure of the initial permutation. That's what let us argue that we could represent it with a small number of parallelograms, right? With a sort of compressible blocked version of the permutation. So we're paying a small price here because what we're saying is what used to be something we could represent with one of those blocks, we're now going to pay the price of representing it with 2 blocks instead. But what we get in return is better performance because we don't have to do as many linear scans. That's the basic idea. Okay. So if we are going to do something like this in order to force a situation where we never have to scan 4 or more times, then what we need is an iterative algorithm that will repeatedly split until this is the case. Okay, so if we start with an initial situation where sometimes we require 4, 5, 6, 7, 8, or 9 scans or something like that, we need to keep splitting until that's just not true anymore. We need to keep splitting until the maximum number of scans is less than 4, is 3 or less. Okay, so let me be more precise in describing exactly that process. So here we go. So we're going to say, here's an iterative algorithm until all the Q runs have weight less than 4, right? Their weight is equal to the number of set bits in P at those same offsets, right? So until all Q runs have weight less than 4, in other words, there's no position in there that requires 4 or more scans. So until all of them have weight less than 4, we'll, first of all, pick one of the bad ones. So we'll pick one of the Q runs that has weight that exceeds this threshold, so greater than or equal to 4. And we'll split it. And the way we split it is by setting more bits. So specifically, we'll set a bit in Q in such a way that this becomes 2 smaller runs. One of them is going to have weight 2, and the other is going to have weight greater than or equal to 2. Okay, so for example, if this is the run we've decided to split, so this run here, I'm showing only an excerpt from P and Q, but these are, parallel portions of P and Q, so the same offsets in P and Q. And so here's a Q run. And if we just look up at P and count the number of set bits inside that run, we see 1, 2, 3, 4, 5, 6. It has weight 6, this Q run. Well, weight 6 is too large, right? We want all the Q runs to have weight less than 4. So we need to split it. So where do we split it? Well, I'm saying we should split it so it becomes 2 smaller runs, one of weight 2 and another of weight greater than or equal to 2. So I guess if we start from the left, if we split it there, we'll end up with this run, this Q run here, which will have weight 2. And then this Q run, oop, I went too far. This Q run here, which will have weight 1, 2, 3, 4. Okay? So initially we had a Q run of weight 6. We just split it up into a Q run of weight 2 and another Q run of weight 4. All right. And we're not done, because if we are going to set a bit in the Q bit vector, remember P and Q have a relationship. We need to maintain that relationship. We'll have to set whatever its preimage is in the P bit vector. So we're not done until we've also set its preimage with respect to P. Okay? So if we just iterate this process again and again and again until we reach a point where all of the Q runs are under our threshold, right? None of them have 4 or greater weight, then we can declare victory. But it's not yet clear whether this is a procedure that's going to stop. And furthermore, it's not clear if the number of times it's going to split runs into smaller runs is going to perhaps cause a problem. Like, for example, are we still going to be guaranteed to have a number of runs that's big O of R, right? Okay, so this isn't clear yet. We have to prove to ourselves that both these things are true, that it's going to finish and that the final number of Q runs is still going to be big O of the initial number of Q runs. In other words, we only increase the number of Q runs by some constant. Okay, so let's prove this to ourselves. All right, so I've got the algorithm that I just described up there in the upper right in that blue box. And the proof idea about how we're going to do this is we're going to consider 2 things that change as the algorithm proceeds. Right, so the algorithm is going to iterate until it's done. At every iteration, 2 things happen, right? So, well, perhaps more than 2 things happen, but 2 important things happen that are useful for this proof. So first of all, each time we're going to set a new bit in the P bit vector, right? Because of this instruction right here, right? So at each iteration, we're going to set a bit in Q that wasn't set before, and we're going to go to P and set its preimage, which also wasn't set before. So we're going to set a new bit in Q and a new bit in P at every iteration. So at every iteration, the number of set bits in P increases by exactly 1. Also, we're going to increase the number of Q runs that have weight at least 2 by at least 1. Okay, let me explain that. So looking back at this example from before, recall that we initially had 1 Q run of length 6, but when we set this bit, we ended up with 2 Q runs, one of weight 2 and one of weight 4. Okay, so you can see clearly in that example, we directly increased the number of Q runs with weight at least 2 by 1. Initially there was 1. When we were finished, there were 2. And in fact, there's a small additional consideration that you have to think about, which is the reason why I have to use this phrase "at least" here, which is that when we go to do this very step here that we were just discussing, in other words, when we go to set the preimage of that bit in P, that might also, or that will also, increase the Q weight of some run somewhere, right? There's some other Q run that happens to be the one that overlaps that bit that we set in P. Its weight goes up by 1. So it's possible that more than one Q run achieves this weight, that we increase the number of Q runs with weight at least 2 by more than 1. But that's not so important for the proof. The main thing for the proof is that we increase it by at least 1. Okay? So if these two things are true, in other words, if at each iteration we increase the number of set bits in P by 1, but we also increase the number of Q runs that have weight at least 2 by at least 1, then something eventually has to become true such that we know we're going to stop, right? In other words, a stopping condition will eventually become guaranteed. Let me explain, right? So if we start with R being the number of set bits, I like to use R because that corresponds to the number of runs in the BWT, and that gives us our initial permutation, right? The initial number of blocks in the permutation is the number of runs in the BWT. So if the initial number of runs is R, then iterating this algorithm R times would result in a situation where, first of all, there are 2 R bits that are set in P, right? Because initially there were R, and then we set 1 additional bit in each iteration. So at the end of R steps, there must now be 2 R set bits. And there must be at least R Q runs with weight at least 2. Okay? Right, because at each step we increase the number of Q runs with weight at least 2 by at least 1. Right, so after R steps, there must be at least R Q runs with weight at least 2. But that is a situation where we must now stop, right? For sure, we can now stop, because if it's true that there are 2 R set bits in P, and there are, like, let's say exactly R Q runs with weight at least 2, that means we're done because all the set bits are in Q runs with weight at exactly 2. Right, in that situation. All right, so we have to stop here or earlier, right? Because if at any point all of the Q runs have weight less than 4, then we can stop. But for sure, by the time we get R iterations in, we can stop, because just thinking about what the situation would be R iterations in, we have to have 2 R set bits, and we have to have at least R Q runs with weight at least 2. So for sure, we can stop at that point. Okay? As a corollary, this means that we are going to, at most, the number of splits we're going to perform is also at most R. Right? We just argued that we have to be done by the time we've done R iterations. So if we start with there being R Q runs, we're going to finish with there being at most 2 R Q runs, which means that we're going to at most double the number of entries in our move structure table. Okay? Because the number of splits we do is also the number of rows that we are adding. Okay, so just as a visualization, when we do splitting, we are increasing the number of rows in the move structure. So if we look at this one specific split that we illustrated earlier that's at the bottom, that results in what used to be just 1 row in the move table becoming 2. So there used to be 1 row of length 9, and we end up with 2 distinct rows, one of length 3, which is this skinnier parallelogram on the left, and then one of length 6. Okay. Notice something also that's happening that might feel a little weird, right? Because the initial set of parallelograms, right, the initial block permutation, comes directly from the runs in the Burrows-Wheeler transform. Now we're splitting some of those runs, right? We're splitting some of those entries in the move table, which kind of pulls apart the idea of a run in the BWT versus a row in the move structure table. Now there actually could be that 1 run in the Burrows-Wheeler transform corresponds to multiple rows in the table. So like just reflecting back, remember the P and the Q bit vectors correspond to L and F, right? The Burrows-Wheeler transform and then the F column of the Burrows-Wheeler matrix. So when we took this initial block, this initial parallelogram, and split it into 2, we are taking something that used to correspond to this entire length 9 run in the Burrows-Wheeler transform, and now we split it across 2 rows. So those 2 rows of the move table both kind of describe 1 run of R's with respect to the BWT. It's just we split it into 1 block of 3 and 1 block of 6. Okay, so the argument that I made here, I used particular constants. I said that we were trying to keep all the Q runs as having weight less than 4. and that at each iteration we made a new queue run with weight at least 2. You can replace these numbers with variables. So instead of saying 4 and 2, you could say 2D and D. And now this thing D is something that you can pick. So you can pick a D that's greater than or equal to 2. And the same argument applies, but sort of more general, right? So the larger the value you pick for D, the quicker you would expect this whole algorithm to finish. And indeed, you get a guarantee that's tighter and tighter as you increase D to larger numbers. I'm going to, though, not go over those details. Those details are in this paper cited at the bottom of this slide. So with that, we now know that even though we couldn't bound the number of scans before, now we can. And we can bound the number of scans by a constant because we get to pick this constant D, or we could, such that 2D becomes the bound, or the way we explained it in the particular proof we did, we bounded it by 4. We said that we would never scan 4 or more times. So we can put a constant bound on that, which means that we can now get to constant time permutations. And because we don't increase the number of rows in the move structure by more than a constant factor, we kept our big O of R space bound as well. So now we have the explanation for why it's possible to achieve best of both worlds, right? As long as we're willing to add some extra rows to the move table, a constant multiple additional rows to the move table, we can achieve these constant time queries. And so in that way, that's why the move structure is able to achieve the best of both worlds result that the R-index couldn't achieve. The R-index couldn't achieve that similar combination. However, there's a small asterisk on this, which is that constant time query that we're doing, where we're able to run the permutation, including we're able to run kind of like composed and nested permutations, a whole chain of permutations. We know that if we have the k and the I to begin with, we can compute the k prime and the I prime in constant time. That's what we covered in this lecture. However, it also means that in order to do the very first one in that chain, we needed to know k and I at the beginning. And this is not the same as the R-index LF mapping query, for example. The way we typically do LF mapping queries, we don't need to know two things. We just need to know one thing. We just need to know the offset where we're starting, and the LF mapping will tell us the offset where we map. In this case, we need a little bit more information. We need to know the offset where we're starting and what's the ID of the run that contains that offset. And it could be that you need to do a little extra work in order to determine that, and this bound is not counting that extra work. This bound is assuming you have all that information to begin with. Now, this is usually a kind of a reasonable assumption. So if you look at the way pattern matching algorithms with respect to compressed indexes usually work, you might think of the very first iteration as being like a range that includes the entire structure, the entire Burrows-Wheeler matrix, in which case it's kind of obvious which are the offsets and which are the run IDs of the beginning and the end of that range, right? If you're at offset 0, then you're in run ID 0. If you're all the way at the end, then you're in run ID R-1, I guess, right? You're in the very last run. So oftentimes, the way these algorithms really work, you do know the run ID from the beginning. And this isn't a very important caveat that I'm adding here. But if you don't necessarily know it, you just have to keep in mind, you might have to do a little bit of extra work to begin with in order to find it, and that might not be constant work. That might be a log-log factor or something like that.